In this video, we're going to discuss standard potential. So previously, we discussed that you could set up a voltaic cell where electrons would flow from one half of the cell to the other half. There was a natural favorability for copper to acquire the electrons more than the zinc. So as the copper ions in solution was to bump into the metal, they'd pull electrons in. This would pull electrons through the wire, and it would pull them out of the zincs on the end, causing those zincs to break off as zinc 2 pluses. There's a general flow of electrons from the anode zinc side to the cathode copper side. How strong is this flow, though? What happens when we change to different metals? When we think about our metals, you can imagine some energy. I have some zinc here, and it's going to lose electrons. Those electrons can flow down to the copper. So I have copper 2 plus here. They'll flow down to make it into copper metal. Well, much like water flowing down through a water wheel or a turbine, if it flows a little bit, it has a little bit of push. But if it flows steeper, say down here to silver plus, becoming silver as the electrons flow to it. Well, a waterfall has a lot of force when the water hits the bottom. But a small flow of water just over one step on a porch doesn't have a lot of force. The steeper the decline in the attraction, silver being far more attracting to the electrons than the copper, and both of them more than the zinc, as a result, those electrons flow more readily and more aggressively towards that silver. They have more force. Well, this can be harnessed for energy, as we'll see later when we relate free energy to our voltaic cells. In this case, though, what's going on here is we need a new term. We need to talk about the potential, specifically the difference in potential. How strongly are our electrons going to flow? A little bit or a lot? For that, we need volts. The volt is our unit for electric potential, and it is equal to 1 joule per coulomb of charge. So for the same number of electrons, you'll have the same amount of charge, but you can get different amounts of energy for them flowing down. If they flow a small decrease, they just won't push as hard. If they flow a large decrease, they'll push harder. Your voltage is a measure of that difference. Well, since voltage is just a comparison difference, we need a reference point. We need something to be the starting point everything is compared to. Is this a big change or a small one? Is this a big change or a small one? Just how big? We need something we can base it all against. And similar to the way that the delta H of formations were created from the elemental materials so that we could define some starting point as 0, we've done that for potentials. The standard hydrogen electrode involves the reaction of aqueous H plus and H2 gas. If something is able to steal electrons from H2 gas, well, then it has a higher potential. It's more positive. If something instead gives electrons to H plus and is not able to steal them from H2 gas, then it has a more negative. It has a lower potential. The propensity for hydrogen to acquire electrons and make H2 gas was set as our standard. The electron potential, the voltage here, is 0. Everything is based against this. Does something's oxidized species want electrons more than H2? Well, then it's going to be higher in potential. It's going to be more positive. Does something want electrons less than H2? Well, then it's going to be lower. It's going to be more negative in potential. There's large tables of this. In Appendix D, in the back of our book, or available on the internet, you can find large tables of standard potentials. So these are all E naught, which is going to be 1 molar ions, or 1 atmosphere for gases, depending on the exact redox reaction occurring. These are all at 298 Kelvin. And so these are potentials at standard states, but that is give us a reference to compare everything to. Hydrogen is indeed our 0 point, and we can see what things are above it. Tin 4 plus, acquiring electrons become tin 2 plus, is a little bit more positive. Tin 4 plus wants electrons just a little bit more than the H2 does. So if the H2 transfers electrons to the tin and becomes H plus, the H plus just isn't able to take them back. That tin wanted them more. There are many, many, many ions here at various charge states in the potentials, both positive and negative. How do we use this then? How do we use these potentials? Well, let's go back to our zinc copper cell. We have zinc solid and copper 2 plus aqueous. That was going to react to make zinc 2 plus aqueous and copper solid. So we have two half reactions. We have a zinc solid going to zinc 2 plus and 2 electrons. I have a copper 2 plus aqueous going to copper solid, and I would have needed 2 electrons as a reactant. Well, this reaction, if we go back up to copper, we'll find that reaction right here. Copper 2 plus 2 electrons makes copper solid, has a potential of 0.34. And as long as we're here, I have my zinc. Well, this is zinc 2 plus 2 electrons becomes zinc solid at negative 0.76. Back to our reactions here, our copper one is written correctly. We have the oxidized material becoming reduced. In fact, all of our standard states in that table are written as the oxidized material becoming reduced. This had an E naught equal to 0.34 volts above the standard hydrogen electrode. In the table, we actually had zinc 2 plus 2 electrons becoming zinc solid. And this had an E naught of negative 0.76 volts. Well, the reaction we actually want for what our cell is doing is the reverse of that. So we have to flip this. There's nothing wrong with that. We can flip a reaction around, no problem. In the same way that if you flip a reaction around, your change in entropy or your change in enthalpy or your change in Gibbs energy will alter their sign, the same is true for your potential. In this case, the reaction we actually want is positive 0.76 volts. So often the tables only show one of your half reactions in the correct direction. The other half reaction you're going to have to flip. In doing so, though, we have found the potential of the two half reactions that are occurring. Well, the overall potential, the E naught for the voltaic cell composed of zinc and copper, is equal to the sum. So 0.76 plus 0.34 for 1.10 volts. What is the voltage of our zinc copper cell that we built? Well, at standard states, so 1 molar solution with the solid metals dipped into them, there will be a 1.1 volt difference. Our other example where I said, hey, silver is a little more wanting of electrons than copper. Let's compare there. My zinc solid plus silver ions would go to silver solid and zinc ions. We'd have two half reactions. Again, my zinc solid is going to go to zinc 2 plus and 2 electrons. Our potential there is the reverse of what's in the table. So it's going to be positive 0.76 volts. But this time, my other ions are the silver. Silver plus aqueous goes to silver solid. I'm going to need 1 electron. Well, first let's find that potential. Go back and look for silver on our table. And here we go. Silver plus 1 electron is going to be 0.8. So our voltage is 0.8. So plus 0.80 volts. Now technically we're not balanced. I'd need to multiply this whole thing by 2 in order to get 2 electrons, 2 silvers, 2 silver solids so that it balances out. And I'd need that up here as well in order to balance my reaction. This, however, does not change our voltage. Remember that our voltage, 1 volt was equal to 1 joule per coulomb. I might put twice as many electrons in, but that's twice as many coulombs. I'll get twice the energy, but I'll get twice the charge. It doesn't affect my voltage. So conveniently, our cell potentials don't need to take this into account. At this point, I simply need to add these 2 voltages together. What is the overall voltage for my zinc silver cell? 0.76 plus 0.80 for 1.56 volts. So indeed, silver wanted electrons more than copper. And so when both of them tried to take from zinc, we find that the silver takes with more force. It has a greater voltage, a greater electric potential. For any combination of reactants performing a redox reaction, we can determine what the potential of that spontaneous transfer of electrons will be. We simply need to find the equivalent reactions from these tables or from another source if it's not one of these ones, compare their potentials, flip the reaction if necessary, flipping the sign of the potential there if necessary, and then summing them together.